Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome to today's lecture for the Material and Energy Balances course. Until now, we have performed calculations related to material balances. We have covered all the fundamentals associated with material balances. We discussed single units, multiple units, systems with recycle, bypass, purge, combustion and biochemical reactions and so on. With that, we have come to the conclusion for the material balances. Today, we will start with energy balances. The second part of the course would be about energy balances. This concept of energy balances is built upon law of conservation of energy, and we will perform calculations similar to what we have done for material balances, and here we will try to account for how much energy is required for processes to function. So, before we start performing energy balance calculations, it is important for us to learn some of the terminologies and also recollect some of the terms which we have already learnt and see how they would apply towards energy balance systems. Let us first start with a review of terminologies that we had already looked at. System is a region which is chosen for study and it is enclosed by an arbitrary boundary which we choose. Surroundings is everything that is outside the system boundary. Boundary is the surface that is drawn to separate the system and the surroundings. Open systems are systems where you have mass crossing the system boundary, therefore there is mass flowing from the system to the surroundings or vice versa. You can have closed systems which have no mass exchange between the system and the surroundings. However, heat and energy work can actually be transferred between the system and its surroundings for a closed system. Hence, when we perform material balance calculations, we would not have looked at closed systems. But now that we are going to look at energy balance calculations, we have to consider closed systems also, because energy is being transferred between the system and its surroundings in a closed system. Property is any observable characteristic of a system. It could be temperature, pressure, volume, mass and so on. So, all these are called the properties of the systems. Steady state is a process where the accumulation is 0 and the terminologies and the properties are not changing with respect to time. Unsteady state is when the system is not in steady state and there is accumulation happening. The system can also exist in equilibrium, which is basically thermal, chemical, mechanical and phase properties of the system being invariant with respect to time. Phase is basically any physically distinct components. So, this could be solids, liquids and gases. Until now, when we perform material balance calculations, we were only looking at each component based on its chemical identity. So, water was not distinguished between water liquid versus water vapor. However, when we perform energy balance calculations, it is important for us to distinguish between water liquid and water vapor, because there is energy associated with phase change. Hence, phases of the components which are involved in the process have to be looked at carefully when we perform energy balance calculations. Let us look at some of the energy balance terminologies which you might already be aware of, but it is important for us to understand and remember these concepts to apply for calculating energy balance equations. Adiabatic system is a system that does not exchange heat with the surroundings during a process. So, this is a perfectly insulated system. So, we would assume that heat transferred between the system and the surroundings is 0 for any adiabatic process. You can also have an isothermal system where the system temperature is maintained as a constant throughout the process. Here, heat exchange would probably be happening between the system and its surroundings to maintain the temperature of the system. You can also have isobaric systems where the system pressure does not change during the process, and you can have isochoric systems where the system volume does not change with respect to time during the process. The variables which we look at while we perform any energy balance calculations can be classified as state variables and path variables. State variables are basically variables that depend on the state of the system and not how the process actually occurs. Example would be internal energy. These are also called as state functions or point functions. Internal energy will depend on the temperature and pressure and composition of a system and does not depend on how the system gets to that particular point. Hence, it is a state or a point function. Path variable is a variable which depends on the process which actually takes place. It is also called as a path function. Example would be heat or work. So, this is important to understand because when we have a state variable, we can actually make assumptions about the reference states which can be used for performing calculations. We will get into the details of that when we perform energy balance calculations. When we talk about path variables, the path taken or the process which happens is crucial for the magnitude of this value. So, let us take this simple example. If I were to move an object from point A to point B through a straight line, there would be some amount of work which would be done on the object for it to be moved. However, instead of moving it in a straight line between A to B, if I were to move it to a point C and then to a point D and then to a point E and then back to a point B, so now I have taken a much longer path and this would require much more work to be done on this object for it to be moved from point A to point B. So, the path or the process which has happened for moving this object from point A to point B determines the magnitude of work which was done on the system. So, these types of processes or variables are called as path variables or path functions. What are the different types of properties which are there when we talk about energy balance calculation? We can have intensive properties. These are the physical properties of a system which do not change with respect to size. So, they do not depend on the size of the system. Example would be temperature, density, viscosity, etc. You also have extensive properties which change directly with size of the system. So, they are directly proportional to the size of the system. Example would be mass or volume. You can convert extensive properties into intensive properties using something called a specific property. Specific property is an intensive property obtained by dividing an extensive property by the total amount or mass of the process material. Example would be specific volume and specific growth rate. If you remember when we discussed biochemical reactions with cell culture, we were talking about growth rate and specific growth rate. Specific growth rate was obtained by dividing growth rate with the biomass concentration or the biomass number. So, this gives a specific property which is an intensive property. Specific volume is also the same. Volume, which is an extensive property, depends on the size of the system. When you divide this volume by the mass, then you get specific volume, which is a specific property, that is intensive property. So, specific volume is actually the inverse of density. As density is an intensive property, you would have specific volume also being an intensive property. When we talk about energy balances, there are different forms of energy which we have to look at. The energy can be exchanged between the system and its surroundings using two different forms. The first one is heat. Energy which is transferred due to temperature difference between the system and its surroundings is called as heat. Conventionally, we will be using heat as positive when it is transferred to the system from the surroundings. Work is the other form in which the system and the surroundings can exchange energy. Energy transfer that happens due to anything other than temperature difference, it could be because of force or torque or voltage, is called as work. Work is positive when it is done by the system and it will be considered to be negative when it is done on the system. So, this convention which we are going to be using for the calculations for the rest of this course is actually arbitrary. Different textbooks use different conventions. It does not matter which convention you use as long as you are consistent with using the same convention throughout your calculations. What is work? Work is, as I said, energy which is transferred due to anything other than temperature difference, which means there could be different types of work that can be done by the system or on the system. You can have a mechanical work, which is the work that occurs due to a mechanical force that moves the boundary of the system. This is calculated as integral f ds, where f is the force and ds is the change in its state. You can have electrical work, which is the work which is done when an electric current passes through a resistance, and this would create some amount of work. So, this is a type of work which we will not look at for our course, because we will be looking at chemical and biochemical processes where this is usually not a major factor. We can also have shaft work, which occurs when a force is acting on a shaft to turn it against a mechanical resistance. So, this would be the shaft work. You also have flow work, which is the work performed on the system when a fluid is pushed into the system by the surroundings. So, this is called as the flow work. So, these are the 4 different types of works, and let us now look at how we calculate mechanical work. Here is a simple example problem. An ideal gas at 300 Kelvin and 200 kilopascals is enclosed in a cylinder by a frictionless piston, and the gas slowly forces the piston so that the volume of the gas expands from 0.1 to 0.2 meter cube. Calculate the work done by the gas on the piston if 2 different paths are used, isobaric process and isothermal process. So, here the actual process itself is the same, the path is different. So, the process is basically expansion of this ideal gas from 0.1 meter cube to 0.2 meter cube. However, the path taken could either be isothermal or isobaric. So, we will look at these 2 different paths and see how the work actually varies when 2 different paths have been taken. First, let us look at an isobaric process. For an isobaric process, we know that pressure remains a constant. So, let us try to calculate work, which would be integral P dV, where you have initial volume to final volume. Now, pressure being a constant can be taken out of this integral, and it becomes P integral V initial to V final dV. So, this is P V final minus V initial. The problem statement gives us that the pressure is 200 kilopascals and the volume is 0.2 as the final volume and the initial volume is 0.1 meter cube. So, solving this, you would get 20 times 10 power 3 joules, which is equal to 20 kilojoules. So, 20 kilojoules is the work that is done. Now, let us look at an isothermal process. For an isothermal process, temperature remains a constant. So, work equation is still integral V initial to V final P dV, but pressure is not being a constant. So, we need to convert this pressure in a way that we can actually represent the volume term also. We have been given that the gas present in the system is an ideal gas. So, using the ideal gas law, we know PV equals nRT. So, this implies pressure is actually nothing but nRT divided by V. So, substituting it there, your W term is integral V initial to V final nRT divided by V dV. So, temperature is a constant, number of moles is not changing because there is no reaction which is happening here. R is the universal gas constant, which is also a constant. So, this equation then becomes nRT times integral of V initial to V final dV divided by V. So, this can then be solved as nRT times ln of V final by V initial. So, integrating and applying the limits, we get this equation. Now, let us substitute the values for each of these things. So, we do not know the value for the number of moles, however, we can calculate it using the ideal gas law for the initial condition. nRT equals PV, which means N equals PV by RT. So, using the initial pressure and volume, so we will assume this to be initial pressure and volume. So, we can calculate N. So, initial pressure is 200 kilopascals, 200 times 10 power 3 pascals times initial volume is 0.1 meter cube divided by R in SI units is 8.314 times temperature for the initial condition is 300 Kelvin. So, using this we can calculate N as 0.00802 kilomoles. So, now that we have N, we can calculate the value for W. We already know the value for R, we know the value for T is 300 Kelvin and Vf is 0.2 and Vi is 0.1. So, we basically can calculate it as 0.00802 times 8.314 times 300 times ln of 0.2 divided by 0.1. Solving this, we can calculate W as 13.86 kilojoules. So, for an isothermal process, the work which is done is 13.86 kilojoules compared to an isobaric process where the work done is 20 kilojoules. This example clearly shows that work is a path function, and although the process itself was the same where ideal gas was expanded from 0.1 to 0.2 meter cube, because of the process and the path which is taken for the process, the values for W were actually different. For an isobaric process we got 20 kilojoules versus an isothermal process where we got 13.86 kilojoules. Let us move on to the next concept. Other than the two forms of energy, heat and work, which are the ways energy is transferred between the system and its surroundings, there can actually be three different forms of energies which are inherently possessed by the system itself. The first type of energy would be the kinetic energy. Kinetic energy is the energy possessed by a system due to translational motion of the system as a whole relative to some frame of reference. This can be calculated as half mv squared, where m is the mass of the system and v is the velocity at which it is travelling. You can convert this term, which is an extensive property, into an intensive property by calling it as specific kinetic energy by dividing this kinetic energy value by the mass of the system. Other than kinetic energy, you can also have potential energy for the system, which is the energy possessed by the system due to the position of a system in the potential field. So, this is calculated as mgh, where m is the mass, g is the acceleration due to gravity and h is the height in which it has been placed in the positional field. So, you can convert potential energy also to a specific property by dividing it by the mass of the system, giving you specific potential energy. Other than kinetic and potential energy, the system also possesses something called as internal energy. All the energy that is possessed by the system which is not explained by the kinetic or the potential energy is called as the internal energy. This is the thermodynamic energy of the system. Specific internal energy can also be calculated as the internal energy divided by mass. So, let us look at a couple of example problems where we try to calculate kinetic and potential energies. Here is the example problem for kinetic energy. Water flows into a process through a 2 centimeter inner diameter pipe at 2 meter cube per hour. Calculate the kinetic energy of the system in joules per second. So, let us perform these calculations. We know that kinetic energy is calculated as Ek equals half mv squared. We have to find what the value for m is and what the value for v is, so that we can calculate the kinetic energy. So, m would have to be calculated from the volumetric flow rate. So, here we have m dot or mass flow rate, which we can calculate from the volumetric flow rate. We know that the volumetric flow rate F is 2 meter cube per hour. This implies mass flow rate would be volumetric flow rate times density. So, density of water is 1000 kilograms per meter cube. So, you get 2000 kilograms per hour. However, the question asks us to calculate kinetic energy in terms of joules per second. So, this hour term would have to be converted to seconds, thereby our mass flow rate becomes 2000 kilograms per hour times 1 hour contains 3600 seconds, giving you a value of 0.556 kilograms per second. So, this is your mass flow rate. Now, we need to calculate the velocity. If you remember, in one of the earlier lectures I had described how we can calculate linear velocity from volumetric flow rate. what we need to do is divide volumetric flow rate by cross sectional area to get the linear velocity. So, we will do that. Velocity is equal to volumetric flow rate divided by cross sectional area. The cross sectional area of a pipe with an inner diameter of 2 centimeters would be pi r squared, where r is 0.01 meters. So, diameter is 2 centimeters, which is 0.02 meters. So, radius is 0.01 meters. So, you get the cross sectional area as pi r squared. Volumetric flow rate is 2 meter cube per hour. So, from here we can get the value for velocity in terms of meters per hour. We still need to convert it to meters per second. So, we will convert that as 1 hour divided by 3600 seconds, giving us a velocity of 1.77 meters per second. Now that we have the velocity for the water flowing, we can calculate the kinetic energy as half times 0.556 times 1.77 squared, giving us a final value of 0.870 joules per second. So, this is the kinetic energy of the system. So, we will move on to the next example problem where we try to calculate the potential energy. According to the problem given, crude oil which is 220 meters below the ground is being pumped to a 20 meter above the ground level. So, let us assume this is the ground level. So, from here we go all the way down to 220 meters below the ground level, and this is being pumped to a level where you reach 20 meters above the ground level. So, this would be used as minus 220 meters, and this would be given as positive 220 meters. Let us now calculate the change in potential energy, which is delta EP equals mg delta H. So, this value would be 15 kilograms per second times acceleration due to gravity, which would be 9.81 meters per second squared, times delta H, which is from the final value of 20 meters and initial value of 220 meters below the ground level, we get it as 240 meters difference. So, finally, we can calculate this value to get 35.3 kilojoules per second as the change in potential energy during this process. With this, we have performed example problems which are simple enough where we can calculate kinetic and potential energies. Let us now move on to the third type of energy which is possessed by a system. It is called the internal energy. Internal energy is a point or a state variable, which I had already mentioned. So, this is an important property which we will exploit when we perform energy balance calculations throughout the course. It is a macroscopic concept that accounts for all the molecular, atomic and subatomic energies. All forms of this energy will follow the microscopic laws of conservation for dynamic systems. This internal energy is calculated based on pressure, temperature, volume and composition of the system. As I had already mentioned, internal energy, which is an extensive property, can be converted to an intensive property called as specific internal energy. When you have a system which is in a single phase with single component, this specific internal energy is actually a function of temperature and the specific volume. When you differentiate this equation, what you would end up with is differential of u cap, which is the specific internal energy, would be equal to dou u cap dou T times dt plus dou u cap dou V cap times dV cap. So, here in the first term you are assuming specific volume to be a constant, and in the second term you are assuming temperature to be a constant. The term dou u cap dou T at constant volume is called the heat capacity or the specific heat capacity at constant volume. So, this term is used when we calculate change in internal energies. The second term, which is dou u cap dou V cap, is usually negligible because change in internal energy is almost 0 when the process is isothermal. So, for this reason the second term can be eliminated and the equation can be simplified to du cap equals Cv dt. From this differential equation which we got, we can calculate the change in specific internal energy. So, changes in specific internal energy will be obtained by integrating the equation we had. So, which would be integral of du cap giving you delta u cap, which is u2 minus u1, will be equal to integral of Cv dt, where you move from temperature T1 to T2. So, now we need to understand that internal energy is not an absolute value. You cannot calculate an absolute value for internal energy. You would only be able to calculate the difference in internal energy. So, from state 1 to state 2, the difference in internal energy can be measured or calculated. We cannot identify the absolute values. So, when we perform calculations or when we look at tables, the values which are given for internal energies are usually with a reference point, and it is given as a value relative to that reference point. Integral equation which we have given here will not be valid when phase change happens. So, what happens here is this particular system we have assumed as a single phase system, and therefore, we can use this equation only when there is no phase change. If we have phase change, there is an inherent change in internal energy associated with phase change, and that needs to be accounted for separately, and it cannot be brought into this integration. So, when we talk about calculating specific internal energy, let us see a simple example problem which will help us understand this. Let us see if we can identify the change in specific internal energy for this simple system. Can you tell me what the change in internal energy would be for a constant volume system if 1 kilogram of water at 100 kilopascals was heated from 0 degree Celsius to 100 degree Celsius and then cooled back to 0 degree Celsius and 100 kilopascals. Think for a second, you do not need to do any calculations. What I had told you earlier is internal energy is a point function or a state function. It depends on the state at which it is present. So, for this process you start from an initial point, go to an intermediary point, and then you come back to the initial point, which means the total change in internal energy would be 0 for this process. For ideal gases, internal energy is a function of temperature only. It does not depend on any other property. Pressure will not affect internal energy. Total internal energy of a system which contains n components can be calculated as U total equals sigma of mi times U cap I, where U cap is the specific internal energy and m is the mass of that component, and the multiplication product of mass times the specific internal energy of that component will give you the total internal energy of that particular component, and summation of all the internal energies of the different components will give you the total internal energy of the system. Let us look at an example problem. It is a simple example problem to calculate change in internal energy. What is the change in internal energy when 10 kilomoles of air is cooled from 60 degrees Celsius in a constant volume process? You have been given that Cv for air is 2.1 times 10 power 4 joules per kilomole degree Celsius. From the integral equation we got delta U equals integral Cv dt. Integration happens from T1 to T2. So, here initial temperature is 60 degrees Celsius and final temperature is 30 degrees Celsius. Your Cv value is given as 2.1 times 10 power 4 dt. So, this is calculated as 2.1 times 10 power 4, and this would be 30 minus 60, giving you delta U as minus 6.3 times 10 power 6 joules. So, this is the change in internal energy. What you observe here is the delta U is negative. So, this is because the system has actually been cooled from 60 degrees Celsius to 30 degrees Celsius. When temperature difference is negative, you would end up with an internal energy, which is change in internal energy, also being negative. So, let us move on to the next concept, which would be the enthalpy. What is enthalpy? Enthalpy is the measure of total energy of a thermodynamic system. It includes the internal energy and also the energy which is required for making room of the system by displacing the environment so that it can establish its volume and its pressure. So, this enthalpy is also called as the thermodynamic potential and is also a state function. However, it is also an extensive quantity which can be converted into an intensive quantity by dividing it with mass to get specific enthalpy. So, enthalpy is given as U plus PV, where U is the internal energy, P is the pressure and V is the volume. As I already said, specific enthalpy, which is the intensive property, can be calculated as H cap equals U cap plus PV cap. Let us consider a system which is a single phase single component system. This specific enthalpy which we looked at would be a function of temperature and pressure. So, if we were to differentiate this equation, you would get dH cap equals dou H cap dou T at constant pressure dt plus dou H cap dou P at constant temperature dP. So, this term which is there in the first part of the equation, which is dou H cap dou T at constant pressure, is called as the heat capacity or the specific heat capacity at constant pressure, which is also represented as Cp. The second term dou H cap dou P at constant pressure is usually negligible when pressure differences are small. At lower pressures, this term can be removed for all processes. When we are calculating changes in enthalpy, we need to remember that we can integrate this equation to get the difference in enthalpy, which would be delta H cap equals H2 cap minus H1 cap equals integral of dH cap from H1 cap to H2 cap would be equal to integral Cp dt, where the integration is done between temperature 1 to temperature 2. Integral equation again will not be valid when there is a phase change. Just like we had the specific internal energy, specific enthalpy also changes with respect to phase change. So, when there is phase change, we cannot directly use this integration equation that has been given. At high pressures, the dou H cap dou P term which we looked at is not negligible. So, this would also be a factor that needs to be accounted for. This value of dou H cap dou P at constant temperature is actually evaluated from experimental values. So, it cannot actually be calculated using some equations. For ideal gases, enthalpy is a function of temperature only, thereby the second term, which is dou H cap dou P at constant temperature, goes to 0. So, the equation which we have, integral Cp dt, is valid for all ideal gases as long as there is no phase change. So, when we talk about calculating enthalpy, we need to understand only differences can be calculated, not the absolute values. Just like internal energy, when you look at values given in tables and values you find in textbooks, these are usually in reference to a reference point, relative to a reference point. It is not the absolute value. So, you should also understand that the total enthalpy of a system which contains more than one component would be the summation of the enthalpies of the individual components. So, the enthalpy of individual component can be calculated as the mass of the component times the specific enthalpy of that particular component, and the summation of all these enthalpies will give us the total enthalpy of the system. Here is one simple example problem which will help us understand how to calculate enthalpy for a system. The air you breathe is immediately warmed up from ambient temperature to 37 degrees Celsius before entering into your lungs. Calculate the specific enthalpy change when the temperature of air is raised from 20 degrees Celsius to 37 degrees Celsius. Assume that air is bone dry and the value for Cp of air is also given. So, what you see here is a polynomial with respect to temperature given as the value for Cp. So, we know that we can calculate delta H cap as integral Cp dt from temperature 1 to temperature 2. So, here initial temperature is 20 degrees Celsius and final temperature is 37 degrees Celsius. We have been given the Cp value as 28.94 plus 0.4147 times 10 power minus 2 T plus 0.3191 times 10 power minus 5 T squared minus 1.965 times 10 power minus 9 T cube times dt. By performing this integration and applying the limits, we will be able to calculate delta H cap as 494 joules per mole. So, with this calculation, we have come to an understanding of how to calculate specific enthalpy change for a system. Now that we have learned the fundamentals and some terminologies associated with energy balances, let us move on in the next lecture where we talk about energy balance calculations, and we will get some introduction on how to perform energy balance calculations and what is the principle behind energy balance calculations. Until then, thank you and goodbye.